So a question on the practice quiz. First thing I do is look at that C9. It gets me to 20, right? Well, it's a little awkward. Maybe not. I'm gonna go 8 because I'm gonna add that chlorine. That chlorine takes the spot. 12. And I'm gonna look at this and say, well, I must have what functional group? A benzene ring. Yeah, so I'm gonna put that on there. And it says just 2 hydrogens. Well, that tells me I probably have some electronegative group. And notice, what are they? They're doublets. So these 2 split into a doublet from those 2. These 2 split in from a doublet from the other 2. So without anything better to do, I'm gonna put my electronegative group here, just because the other day when we had like nitrotoluene or something up here. Now, how many degrees of unsaturation did my ring burn up? 1, 2, 3 with the double bonds, 4. 4 from 6 leaves 2. And how many more carbons do I have? I start out with 9 and I've burned up 6. That means I have 3 carbons. Should I do that? 7. 4 and what makes 7? 4 and what makes 7? 3. Now I don't have any hydrogens left over for this thing. But I still didn't burn up all my degrees of unsaturation. So now let's count the degrees of unsaturation. I got a ring. I got 3 double bonds. Well, that's horrible. 6. Got the ring. 1, 2, 3, 4, 5, 6. So now I think that's probably it. I just handed out a table of IR stretching frequencies. This thing here. And the other day when I was looking at this, it made me angry. My IR table doesn't go past 3,000. But my stretching frequency does have a triple bond there. And we could probably just as easily put the methyl group here and the chlorine here, but I'd give you full credit. Now let's look at the carbon-13 NMR numbers. I have 1, 2, 3, 4, 5, 6, 7 signals. I have 9 carbons. Some of these might be equivalent. What did I say? 7 signals? 1, 2, 3, 4, 5, 6, 7. Quintet. That would be this one, because N equals 3. Quin. That means 5, right? What? 5. Singlet? Maybe a singlet. 1 hydrogen, a doublet. 1 hydrogen, a doublet. 88 is the quintet. Let's make that Q a quartet. How do you spell quartet? Yeah, so it all makes sense. You're welcome. Good question. Any other questions? No questions? All right. And this chapter is on ether and alcohols and epoxides. I'll have to wear the shirt that Shelby got me. I have all these t-shirts and I never wear them because now that I'm old, I need a pocket for my glasses. So good examples of ethers. This one's symmetric, so we can easily name it via alky group. This is a common naming convention, diethyl ether. You see the 2 ethyl groups. We can also use a common naming system and say methyl phenyl ether. And here is tetrahydrofuran, and it's a cyclic ether. And you just got to memorize that name. And of course, we call this THF, which you've seen before with your anti-Makarnikov hydration of a double bond with the SYN stereochemistry. So some common things you ought to know already. Ethers have an oxygen, sp3 hybridized, gives it a dipole. So most ethers have a dipole-dipole intermolecular force due to the polarity of this bond. Although that ether has that polarity, doesn't seem to give it a lot of intermolecular force like hydrogen bonding. Hydrogen bonding gives alcohols an unusually high boiling point. So water and ethanol both can hydrogen bond. So super low molecular weight, 18. Boiling point of 100. That's off the charts. Now we get to dimethyl ether, 46. So these are nice. They're all like nominally the same. Propane, diethyl ether and ethanol, and we see this big change here. This is due to hydrogen bonding. And so it says here, similar to alkanes of comparable molecular weight, that dipole moment has some effect there. You can see a much higher boiling point. Granted, negative 25 degrees Celsius seems pretty cool. All right, our next set, all nominally around 73 molecular weight. We have our THF, diethyl ether, and just regular pentane. And these are really super close. This is a little higher, probably because this ring keeps the ends from flopping around, makes it a little more rigid, and it can pack up, has more opportunity for London dispersion forces to grab another molecule. Ethers cannot hydrogen bond with each other, so they have lower boiling points than alcohols. Ether molecules can hydrogen bond with water and alcohol, so ethers can absorb moisture out of the atmosphere. Chemists work real hard to get their ethers very anhydrous, probably for all that organometallic chemistry like Grignard reactions. Ethers are widely used as solvents because they can dissolve nonpolar and polar substances. They also are fairly immiscible water, even though they can hydrogen bond with water. You'll recall from your extraction lab, the diethyl ether was floating on top of your separatory funnel. The aqueous layer was down below. Looking through this list, here's one that might want to sink to the bottom of the separatory funnel. It has a density a little lower than water. I can imagine this thing being a hassle in forming emulsions and not wanting to separate real well. Gravity's not going to want to separate it as well as some of these others. Ethers, they are unreactive towards strong bases. And remember, a Grignard is about the strongest base known to mankind, because if you let it get around water, it gets protonated and typically forms an alkane, which I say is the weakest acid known to mankind. So ethers can solvate some ions. Here's ether solvating a cation. Doesn't solvate well an anion there. Anionic substances such as lithium iodide is moderately soluble in ethers because of the small lithium cation is strongly solvated by ether's lone pair. Unlike alcohols, ethers cannot serve as hydrogen bond donors, so they do not solvate small anions. Reminds me of that SN2 chemistry, that SN1 chemistry with the protic and aprotic. For SN2, you wanted an aprotic solvent because it doesn't impede a nucleophile. So those Grignard reagents, they were special in that you had to do them in ether. THF or diethyl ether is what you use. Can't use benzene, can't use toluene, can't use hexane, cyclohexane. They only work in ether. And a guy by the name of Whitesides figured out why that is. Grignard reagents form a complexation of an ether with a Grignard reagent, stabilizes the reagent and helps keep it in solution. And here is something I alluded to earlier, the anti-Makarnikov hydration of a double bond. The first thing you added was this BH3THF, and then you would add the hydrogen peroxide under basic conditions. Electrophiles, the ether's non-bonding electrons stabilize the borane. Crown ethers, they're kind of a special thing. They work as catalysts a lot. Crown ethers can complex metal cations in the center of the ring. The size of the ether ring will determine which cation it can solvate better. Complexation by the crown ethers often allow polar inorganic salts to dissolve with non-polar organic solvents. So there's interesting chemistry done with these where the metal catalyzes various reactions. We don't have to learn any of them. So you've heard me name some of these, this common naming convention. Name the two alkyl groups attached to the oxygen and add the word ether. Real straightforward. Name the groups in alphabetical order. Symmetrical, use dialky or just alky. Diethyl ether or ethyl ether. T-butyl methyl ether or methyl T-butyl ether. Guess I'm confused. T before M or B before M? or M before T. Makes me want to go look at the slides at the beginning of the fall. IUPAC names, alkoxy alkane names. So in the fall, I try and start using methoxy, ethoxy, because they show up in our elimination reactions, some of our substitution reactions, the Williamson ether synthesis. And so to properly name an ether under IUPAC naming convention, we take the more complex alky group is the alkane name, the smaller group, which is good because we know methoxy, ethoxy, butoxy. So a cyclohexane alkoxy might be difficult to come up with a name. So the smaller group becomes the alkoxy. So here we name this 2-methoxy, 2-methylpropane. Here's a propane, it's got a methy substituent and then a methoxy substituent. Methoxy cyclohexane. Those are the IUPAC names. And here's a slide I hate to put up. Heterocyclic, there's a 3-membered ring, but every atom isn't carbon. We have an oxygen, so we call it a heterocycle. This one, the only thing you need to know is this is the basic building block of an epoxide. The rest of these, I never ask for any points. Dioxanes are interesting because halogenated dioxanes are like the contamination in some Superfund sites. Paper mills and certain things generate halogenated dioxanes that are just horrible. That looks like a good place to end.